Okay, let's get started. Hey y'all, welcome on this lovely Tuesday morning. This is officially your last week, 474. For some of you, I was just talking to our very own Brooke Wallace, and this is her last week of university. Actually, out of interest, how many of you are graduating this fall? Besides Brooke. At least you, if you don't raise your hand, no one else can. Is that it? I very much doubt that. There's got to be at least one more person here graduating. How about it? What if I rephrase it, hoping to graduate if you can get past me? Yeah, maybe that was a little too mean. Especially since I'm asking you guys to fill out the course evaluation. I sent an announcement on campus. I know it's a pain in the ass. I mean, they used to do it here in class, which I think makes a lot of sense. But I really encourage you to do it because I really take them seriously. I read them very carefully. I take criticisms to heart. If there's something I did that you liked, that's good to hear. But if there's something that you didn't like, that you think can be improved, I really will actually employ that, believe it or not. You know, so some of the things that I'm doing are based off of student advice. You know, so please get on Canvas, you know, and do it. You know, you can even wait until after the final, and you can make up your mind how nice and mean I am. And your evaluation can be based on that. All right. So today we get to finish Biochem, or start finishing Biochem 1 with Chapter 18. I always kind of half-heartedly joke with you guys on every chapter. It's my favorite chapter. I really do love Biochem 1. I think you guys can see that now. I just think it's so interesting. There's so many topics, as opposed to Biochem 2, which is good. For me, it's just a little less awesome. I really do love Chapter 18. I think it's just such a wonderful way of bringing things together that you guys have learned to understanding how, you know, arguably, you know, when you think of what are the most important molecular machines in the cell, what comes to mind? I mean, obviously the ribosome is immediately going to come to mind. It certainly counts as a machine. It has dozens of subunits. It's made out of RNA. It's of obvious importance. It synthesizes proteins. It's highly regulated. When things go bad, you know, it gets really bad. What else? You know, the polymerases, the DNA polymerase, copying our genome. That's of obvious importance. RNA polymerase, turning that DNA into RNA. But I would certainly place the ATP synthase machine in the top 10 because generating ATP is so fundamental to sustaining life. I believe there was a slide that we discussed earlier, either in chapter 15 or 16, where we talked about how we burn through kilograms of ATP every single day, depending on how much exercise you're doing. Whereas our body merely contains grams of this stuff. So that presents a task to our cells to have to constantly regenerate ATP from ADP and orthophosphate. And you know, how this occurs at the molecular level is no matter how jaded I get and old, I will always find that to be one of the most beautiful things I've ever seen in my life, on par with waterfalls cascading thousands of feet down the great canyons of Yosemite Valley, or the Denali National Park, or the things I've seen in Europe, the great beauty that the world has to offer. there's great beauty in the molecular world too. And so this machine is a beautiful example of that. So we will study it in detail, and then we'll watch some movies, because given the great importance of this, there's a wealth of biochemical and mainly, for this class, structural information that has enabled these beautiful movies to be made so that we can see the conformational changes that are occurring that are absolutely essential to the synthesis of ATP. So the thing you guys should be wondering, if you haven't read the chapter already, is you should be thinking, how do conformational changes in this molecular machine, in ATP synthase, result in taking an unfavorable reaction, a reaction with a delta G naught prime of around 30 kilojoules per mole, and somehow making that favorable. And we know, because we've talked about this already, that that energetically unfavorable event is coupled to something that's even more favorable, which is the dissipation of a proton gradient. So before we can get into talking about how ATP synthase works, the first thing we need to do is discuss how mitochondria are able to generate that proton gradient. And as we've been alluding to in chapters 16 and 17, that gradient is going to be formed by the oxidation of electron fuel in the form of mainly NADH, but also to some extent FADH2. Where does that NADH and FADH2 come from? Well, we know that NADH is generated during glycolysis, catalyzed by GAP dehydrogenase. It comes from pyruvate dehydrogenase, the conversion of pyruvate to acetyl-CoA, which is occurring in mitochondria now. We know that there are 3 steps during the citric acid cycle that are oxidation reduction reactions, resulting in the transfer of high energy electrons from a reduced substrate of the reaction to NAD plus generating NADH. And then we also learned that there was one case where instead of NADH being the electron carrier, it was a molecule called FADH2. And I had told you, but I want to refresh your memories on the matter, that the reason why is because the actual energies that are available in these substrates differs. And so there's a barrier to whether a electron transfer reaction, whether an oxidation reduction reaction is going to be energetically favorable. And as we'll see today, there's a way of actually calculating this. So one word of warning, today is another day of learning how to do delta G naught prime calculations, and therefore delta G. It is the last time you'll have to do this. And we can then see from doing these calculations why it's the case that we can't transfer electrons in that reaction. That was the reaction where I believe succinate is being oxidized to malate. And we'll see from the energetics of that electron transfer reaction why NAD plus cannot accept those electrons in an energetically favorable way. Instead, those electrons have to go to FADH2. One more quick point, and then we'll get into it. The savviest members of my audience, everyone here is savvy, and I'm not just kissing your ass because you're supposed to do your evaluations today. The savviest will say, well, what about the conversion of malate to oxaloacetate? That's also an oxidation reduction reaction. It will involve the transfer of electrons to NAD plus generating NADH upon oxidation of malate and generation of oxaloacetate. We learned last week that it has a delta G naught prime that's crazy positive. It was like approaching 30 kilojoules per mole, extremely energetically unfavorable. However, that's a special reaction because oxaloacetate levels are normally kept so ridiculously low because, as you guys know, oxaloacetate is not only a substrate for the citric acid cycle, it's also a substrate for things like gluconeogenesis and the biosynthesis of other things. And so that's a special reaction where Le Chatelier's principle is really, yes, it's unfavorable to transfer those electrons to NAD+, but the delta G will end up being slightly negative because of the special properties of oxaloacetate in metabolism. Any questions? Should we get into it? Okay, let's do it. All right. So we're now carrying on from where we left off, where we discussed glycolysis and the citric acid cycle. So let's recap where we're at. A carbon-based fuel, the sugar glucose, has been oxidized. It's been oxidized mainly to CO2, right? We've generated CO2 3 times, if you recall. Going from pyruvate to acetyl-CoA generates CO2. Going from the 2 substrates or intermediates in the citric acid cycle, also, I believe it's when isocitrate is converted to alpha-ketoglutarate, and I believe when alpha-ketoglutarate is converted into its product is when decarboxylation occurs. We've made some ATP, but it's really a pathetic amount, and as I've alluded to before, if you think that that amount of ATP is enough to get by on, all you have to do is hold your breath for a mere 15 seconds and see what happens. This is really where the money is made in metabolism. We've generated, from 1 molecule of glucose, we've generated 10 molecules of NADH and 2 molecules of FADH2. And so what's going to happen is those electrons still have energy. Work can be done through the coupling of the release of that energy upon the oxidation of NADH and FADH2. And what we're going to see is that that's exactly what happens in this grand another molecular machine that deserves to be in the top 10, the electron transport chain. And what the electron transport chain is evolved to do is couple the free energy available upon the oxidation of NADH and FADH2 into the generation of a proton gradient in the mitochondria. Okay, so this is a scheme introducing you to the electron transport chain. Maybe this is a good point for me to be very clear that the electron transport chain is detail ridden. And so I'm going to try to help you guys by going quickly through the electron transport chain because there's no real serious mechanism being learned here. Instead, it's a lot of brute force memorization. So I will try to help you, tell you what I think you need to know in terms of that memorization. So let's actually get started. So the electron transport chain is a series of large multi-subunit complexes that have been named complex 1, 2, 3, and 4. So complex 1 is a multi-subunit enzyme that contains, dozens of subunits. It's huge. And what's going to happen is that it's going to bind to NADH. And it's going to catalyze the transfer of those electrons from NADH to a molecule that we are going to talk about called coenzyme Q. Coenzyme Q is an interesting molecule because you can think of it as like a taxi cab. If you think of this whole complex as Manhattan, big, bustling, crazy, complex stuff, and you can think of the electrons as people, you can think of coenzyme Q as Ubers or taxis, taking those electron people around from one complex to another, which is essential to driving the formation of the proton gradient. That's ultimately what we're going to see is in the electron transport chain, there's just going to be a series of oxidation reduction reactions lowering the energy of those electrons until ultimately they're going to end up on molecular oxygen, which is going to result in the formation of a water molecule. Okay? Now you would think by the entire semester I would learn to just reset this thing so that I would not go to sleep so quickly. But stubborn old dogs. All right. So basically what's going to happen is, and by the way, this thing right here is not meant to be an accurate picture. That's not what this thing looks like at all. We'll look at some structures. But what they're trying to show you is that the mitochondria, which you remember, I'll show you pictures in a second, but mitochondria are special organelles because they have two membranes. And because they're enveloped by two membranes, that means that they have something called an intermembrane region. And that intermembrane region is going to be where the protons are pumped. So I'm going to start using that word now. The electron transport chain machinery, these complexes, act like pumps to pump protons from in here, which we refer to as the mitochondrial matrix, into this inner membrane space in between those two membranes. Then what's going to happen is those protons are going to flow through the enzyme we call ATP synthase, and the flow of those protons is somehow going to be coupled to the synthesis of ATP. And I want to give you guys, a hint right now that it's not intuitive. It would have been intuitive if you would have said, "Oh, I know what's going to happen. There's going to be conformational changes that result in stabilization of the transition state and lowering the activation energy barrier." But if you remember when we studied myosin in chapter 9, we learned that myosin, which is also is an ATPase, which means it hydrolyzes ATP, so it's an incredibly similar cousin to this enzyme. And we learned that the equilibrium constant for ATP to ADP was around 1 when bound to myosin. And so what we're going to see is that the coupling of protons flowing through, or I should say the allowing of protons flowing through the ATP synthase, is going to couple unfavorable conformational changes that don't necessarily have anything to do with the equilibrium between ATP and ADP. It's really just prying the jaws open of the active site, allowing the ATP to leave. So that's totally non-intuitive. It's still, frankly, non-intuitive to me because the way these things work are wondrous. But we're still going to get into it and talk about it. So here's a cartoon just trying to show you what the physiology of mitochondria, what the physiology looks like. And they're making the point that, yeah, we've got these two membranes. The outer membrane is shown in yellow, and the inner membrane is shown in blue. And you can see that that inner membrane is folded very much like taking a blanket and folding it over and over and over and over until you have this nice, beautiful folded blanket. And we have all of these different folds. Why do we have this? Why did the inner membrane evolve this way? Well, for those of you who are into folding your laundry and putting it away as opposed to just having a mess, the reason why you fold your blanket is so it can fit in your closet, right? If it was like elongated, where are you going to store that thing? Most of us don't have storage areas that are the size of a king-size bed. So you fold it, right? And you basically fold it down to a much, much smaller size. But that being said, the surface area of the blanket hasn't changed at all. And so that's exactly what's happening here with the inner membrane in mitochondria. The inner membrane is folded over and over and over to maximize the amount of surface area that can be put into the size of the mitochondria. And what this is going to do is it's going to maximize the number of electron transport chain complexes and ATP synthase complexes that can fit into a mitochondria. And actually, I mean, some of this stuff is super fascinating because when people start exercising a lot, these are the kinds of physiological changes that can occur in people. You know, where not only do they start growing more mitochondria per cell, but even the mitochondria physiology can change. Okay. So in oxidative phosphorylation, the process that we're studying, again, that means the coupling of the oxidation of a reduced molecule to the phosphorylation of ATP to generate ATP, the electron transfer potential of NADH and FADH2 is converted to the phosphoryl transfer potential of ATP. That's the energy transduction that is occurring. Remember, transduction is just a fancy word for conversion. Okay, so to describe this in terms of a quantitative measure, and you guys no doubt guessed, delta G, we need some kind of chemistry terms. And that's where the reduction potential is going to come into play. This reduction potential, or the written shorthand is E naught prime, is going to be an actual measure of the tendency of a substance to gain or lose electrons. Right? In other words, it's going to tell me, first of all, oxidation and reduction reactions always occur between a pair of molecules. Right? It always has to be relative to one molecule versus the other. So for instance, I could be a reduced molecule, and if I'm like crazy reduced, right, if I'm just like high octane fuel, then it wouldn't really matter who you guys are in terms of molecules that you choose to be. I would basically have a higher reduction potential than you, meaning would be energetically favorable for me to transfer electrons to you. That being said, even if I was a molecule of mediocre electron transfer potential, there are going to be molecules that still dramatically want electrons, right? And so again, it's all relative to where you land on this table that we're going to look at of reduction potentials. For instance, the most oxidized molecule that we're going to talk about in Biochem 1, and probably in all of biology, is molecular oxygen, right? Molecular oxygen is extremely oxidized. I mean, it kind of makes sense, right? Oxygen, oxidized. You can kind of see where the names even come from. And that means that molecular oxygen is just willing to take electrons from practically anything, okay? And so, therefore, it's not surprising that molecular oxygen is going to be the final acceptor of electrons from all this stuff that we've been talking about. Now, the reduction potential is going to depend not only on the identity of the substance, as I just told you, it also is going to depend on the environment. So here we go again. So what are the other things? And let's think about this. In Biochem 1, what are the things that we discussed that depend tremendously on environment? What's that? Yeah, I heard Ka, like what kind of biochem values depend on environment? pKa or also Ka. And then E naught prime, reduction potential. And then we certainly can throw delta G naught prime in there too, right? That's actually cheating because we know that this is equal to this. And so KEQ is just a more generalized equilibrium constant compared to Ka. So really, off the top of my head, is these two guys that are going to be affected. But really, anything is going to be affected by the chemical environment. You guys have to remember that. Because at the end of the day, we're always making this comparison in free energy between one molecule A, and molecule B, and to decide whether a reaction is going to be favorable or not, or spontaneous or not, we need to calculate the energies of both of these states. And one of the most important considerations is the environment. In fact, as you guys know, that's what determines the stability of the folded state of a protein, the fact that it's in water. And when it's not in water, like a membrane protein, things change. Okay. So now we have to discuss how biochemists can measure the reduction potential of a molecule. And so this is the experimental setup. We're going to have two beakers. We're going to have a wire connecting those two beakers. And then we're going to have a voltmeter, which is basically just an instrument that can measure whether there's current, the magnitude of that current, and the direction of the current. Okay, so do you guys know what current is? It's just the flow, a measure of the flow of electrons, right? Same thing as water flowing through the pipes in your house, right? The more you turn on the water, the more water comes out. That would be, the magnitude of the current. And then, of course, direction is just direction. And then they connect them through this thing called an auger bridge. Auger is solid. It's like a gummy bear. Ooh, I like that better. That'd be pretty sweet. If they did this experiment and they're like, we used gummy bears to connect our two beakers. That would be like a total Dr. K experiment. Okay, so we've got our experimental setup. This is going to be called the reference cell. The reason why it's called the reference cell is always going to be the same no matter what. And in that cell, number one, they are going to add protons in the solution with water to a concentration of 1 molar. So the pH of that is going to be 0, I think. Hopefully. Yeah, it is. Or no. Well, minus 0 is 0. Okay, it is 0. I like it. Okay, so then we're not done. They're actually also, by the way, going to cover these things. I should have mentioned that. They're not going to let these things interact with the air. So they're going to put a little top over this. And so in the gas that sits in between the top of the beaker and the solution, they're going to put 1 atmosphere of hydrogen gas. Now, can someone tell me why are they using hydrogen gas and protons? And what is the major difference between those two things, those two compounds? Yeah, Seth.
Well, the protons are oxidized, the hydrogen gases are reduced.
That's beautifully said. Seth said, he basically was alluding to, these are almost the same thing, but the proton is the oxidized form of hydrogen, whereas molecular hydrogen, or H2, is the reduced form. So we basically have here an equilibrium. Between oxidized and reduced. They're going to be in equilibrium. And one of the things that you have to also understand is that if the H plus picks up electrons through the flow of electrons through this thing, it will become hydrogen gas, and vice versa. Okay? If hydrogen gas donates electrons that flow through this wire over to here, it will become a proton, and undoubtedly then it becomes part of that solution somehow. Maybe it rains, proton rain, I don't know. Kind of And then what about the left beaker? This is going to be our test cell. And so now what we're going to do is we're going to make a solution of molecule X, where molecule X can literally be anything we want it to be, assuming that it can exist in a reduced form and in an oxidized form. That's very, very important. And the pre-equilibrium condition is to create this solution such that we have equal concentrations of the reduced form, X minus, and the oxidized form, X, 1 molar each. And then we just sit back and watch. And one of three things is possible. First, electrons can flow from this solution over here, protonating these protons, resulting in the formation of additional hydrogen gas before equilibrium is achieved. And so what will happen is that voltmeter will start reading some value. And that's what we're going to write down. That value is our reduction potential. And they define, I don't remember whether they define this as negative or the other direction is negative, but that doesn't matter. For now, I just want you to understand that one possibility in the experiment is having electrons flow from X minus through the wire down over here into the solution, the acidic solution, resulting in the reduction of protons forming additional hydrogen gas until equilibrium is achieved, and then everything stops and the voltmeter reads 0. Another possibility is the opposite, where H2 gas becomes oxidized, and those electrons will then flow through the wire. This voltmeter will have a opposite reading, right? Positive or negative, again, we'll figure out which. Those electrons then flow over here, react with molecule X to generate additional X minus until equilibrium is achieved. And that will be the value. Now, if we have, and then third is that the trivial possibility is we're at equilibrium. So if we're at equilibrium, then nothing happens, all right? Boring. Let's say we have a molecule with extreme reduction potential on the left, high octane fuel. That means that it's just got these electrons that it's dying to get rid of, right? To lower the free energy of our system. Those electrons have to move from here to here. And so that's going to result in a really large magnitude on this voltmeter. Whereas if we're starting with a molecule that has relatively less reduction potential, then the voltage is going to be the same sign, just not, the magnitude won't be as great. That's how this is done. Any questions? Pretty clear. So, let's summarize. In any oxidation reduction reaction or redox reaction, one substance is getting oxidized while another is getting reduced. So we are transferring electrons from one molecule to the other. The reduced molecule is getting those electrons. The oxidized molecule is giving up those electrons. In spontaneous redox reactions, electrons are transferred from the substance with the lower, more negative reduction potential to the substance with the higher, more positive reduction potential. This is very important. This is the key to understanding how to perform the calculations we're about to do. So if I have a oxidation reduction reaction, and I don't know how to draw these arrows, I can look at a table of reduction potentials, and I can say that if B is positive and A is less positive or negative, and I get to write my equilibrium like this. And so now what we want to do is we want to figure out how to do this quantitatively, right? We want to actually perform calculations. And so here comes table 18.1. Oh, this is important enough to interrupt the class. I forgot to say this. So a student came up to me earlier and said, hey, do we have to come to class for the final? And the answer is, do not come to the class for the final. I will not be here, right? And the door will probably be locked. You should go somewhere where you have great high-speed internet, right? You should go somewhere that's nice and quiet. You should go somewhere where there is no other biochem students but yourself, right? I take this crazy seriously. Do not test me. You know, I am not on that Discord, as far as you know, right? So just don't do it. You know, it's open book. You guys can absolutely even use Google if you want. I'd recommend not doing that. It takes too much time. And it won't work, by the way, for this exam. But you can do anything you want, okay? Just whatever you do, make sure you are going to be in a place that has backup internet in case something goes wrong. Because if anyone emails me with an amazingly good reason for missing the final, I'm not a heartless person, right? I will give you, what you're going to get is an incomplete, because I don't have time to deal with you, right? I'll have to wait until the holidays and use my Christmas break to write your exam, which will most certainly be a fully short answer. If you love short answer tests like midterms 1 through 3, by all means, go for this, right? So you really want to be careful about making sure that nothing bad happens and you're in a place with internet so you can take this much, much, much easier exam. Okay, you guys? Is everyone cool with that? Does anyone want to ask a question? I'm going to open it at 10. You're given 2 hours, and it closes at 12:10. So that gives you guys a buffer or a window of 10 minutes for whatever reason. Ch18.
So are the tables going to be given on the exam, or should we have?
You'll just have your book ready to go, you know, and if I tell you go to table 18.1, then you'll go to table 18.1. Yeah.
How long does it typically take students?
It's short. Yeah. I mean, there will be students that take the entire 2 hours. There will be students that complete it in as short as 45 minutes that get good scores. But for most of you, I would wager prepare to be, you know, an hour and a half, hour 45. Yeah.
Are there questions going to be shown at once, or is it going to go one by one?
They're all going to be there, meaning you can go back and forth. Because what I want you to do is skip hard questions. I want you to employ the test-taking strategies that we've been discussing. So if you see something that's confusing, I want you to leave it. I also want to give you the opportunity to go back, and if you have extra time, make sure you didn't make a silly mistake. I want you guys to do really well. As you can see, the way this class is structured is the exams are supposed to keep progressively getting easier. Mainly because you're getting smarter. But also, I'm trying to take my foot a little off the pedal because I want everyone to get the grades that you want. You know, and so having an easier final that's worth 40% is a powerful way of doing that. But I want to emphasize this question is not an easy exam if you're not prepared. So for instance, if you haven't watched the Wednesday night session from last week, you are playing with fire. Yeah?
Some professors have us log into like Zoom or something.
Nope.
Okay.
There's no respond. It's lockdown. You are all adults. And I trust you to do the right thing. Which is why I have this policy that if anyone is caught cheating, you will fail. Because, you know, I understand the temptation. Of course I do. It would be a horrible lie if I told you I'd never cheated in my life. But I know that was wrong and unfair, right? Which is why I take this seriously. Okay, let's get back to this stuff because this is important.
Generic question real quick. How do you catch cheaters if you're not monitoring?
I can catch cheaters because their wrong and right answers correlate. And I have software that tells me whose answers are correlating.
Multiple choice.
What?
But it's multiple choice. There are going to be many instances.
In the past, I've seen students that had exactly the same wrong answers. And I know which wrong answers you chose. I know if you chose A instead of B, and so it's easy to figure it out. And in the instances where I caught these students, they instantly owned up to it. They knew. So I have a pretty good track record. Fortunately, it doesn't happen very often. Okay, so we're looking now at a table of reduction potentials for various molecules and compounds. You should look at these and recognize a lot of them. Some of them we haven't discussed yet, but many of these we have. So here's NAD and NADH. Now notice in this table, they actually give us the reduced form and the oxidized forms. Don't be confused by that. And then so here's NADH, alpha ketoglutarate, citric acid cycle intermediate. What else do we have here? Acid aldehyde and ethanol, right? That was fermentation, right? A part of chapter 16 in glycolysis that we studied. Pyruvate, lactate, same thing. Fumarate, citric acid cycle. Well, this ubiquinone thing is Q that we just started discussing, so you haven't seen it yet, but I'll show it to you soon enough. And then here's our good friend, molecular oxygen. Now, as I said earlier, molecular oxygen is just this super oxidized molecule, meaning that in the context of biological molecules, it is always going to be the molecule that wants electrons the most. And so in any redox reaction, that's going to be the molecule that's most, that's going to result in the biggest free energy changes, right, upon electron transfer. And so remember what I said a minute ago in our, in the previous slide, where I said the spontaneous reactions will occur between reduced molecules that have a negative or a more negative reduction potential to molecules that have a less negative or more positive reduction potential. So now we see why. We see that molecular oxygen, which you believe me now is an amazing electron acceptor, has a reduction potential of 0.82 volts. So the way to look at this table is simply to say anything, the electron transfer from the reduced form, and anything that's higher in the table to anything that's lower into the oxidized form that's lower in the table is going to be spontaneous. Okay? In other words, we can say that the transfer of electrons from NADH or FADH2 to molecular oxygen will be favorable. Now that's not biologically relevant. Electrons don't go directly from NADH and FADH2 to molecular oxygen. They go through this electron transport chain. But I'm just making this point that you can still make that calculation nonetheless and calculate what the free energy change would be if that reaction occurs. Okay, so now we get to do some calculations. And I promise you, this will be on your final, not necessarily this question. In the following reaction, which molecule loses electrons, which substance gains electrons, and what is E naught prime? And so, which molecule here is going to gain electrons? Is it pyruvate or lactate? It's lactate, because lactate is the, I think I got that backwards, right? No, my bad, you're right. You guys were right. Because, let's refresh our memories. Or maybe Dr. K refreshes his memory. So because pyruvate is accepting electrons from NADH, NADH is getting oxidized, pyruvate is getting reduced to form lactate. Now, the harder part is what is the E naught prime? This really should read delta. What is the change? So the way to do that is to say, by the way, this is going to be exactly the same as calculating phosphoryl transfer potentials. So if you were very comfortable with that in chapter 15, this is going to be pretty much the same thing. Yeah.
So that's a good question. On the table, which is oxidative, is that the one that's taking the electrons from the other one?
We don't know yet, right? This is just the oxidized form of that molecule. NAD plus is oxidized relative to NADH. That's what that means. Here's a question from Rebecca. So what you want to do to start is we want to go ahead and write out the reactions as shown in table 18.1. So for instance, if you look here, we have NAD plus and NADH have a reduction potential of minus 0.32 volts. So, N plus 2 electrons plus a proton is going to become NADH. And that has an E naught prime of negative 0.32 volts. Definitely want to make sure we're using our units. Then we have pyruvate. It's 2 electrons. Plus a proton. Lactate. Oh, wait, sorry. Lactate. That had a reduction potential of, drum roll please, minus 0.19 volts. And so now the question is, how do we combine these? And it's the same thing as I said with phosphoryl transfer reactions. We have to look at our overall equation for the reduction, oxidation reduction reaction between these two molecules, and we have to find the form that is the opposite as shown in the table. So for instance, I'll first point out that pyruvate is on the left of this equation, and it's on the left of this equation. Lactate is on the right of both equations. That's easy to see, yeah? Then, if you look at NADH, it's actually on the left for the equation in table 18.1, but it's on the right of the reaction where we want to calculate the reduction potential. So all we have to do is rewrite this backwards. NADH becomes NAD plus 2 electrons, proton. Now we can go ahead and start combining these together. 2 electrons and the proton cancel, and then we get our final equation that we want. Pyruvate plus NADH becomes NAD plus lactate. The thing is that whenever you reverse an equation like that, the sign of the reduction potential also gets reversed. Now when I add 0.32 volts to minus 0.192 volts, I'll get a final value of 0.13 volts. Seth?
Wouldn't it have to be 2 moles of H plus? Because there's still an H plus on the left-hand side. If there's only 1 mole, then both.
There's no H for the pyruvate one.
Oh. Okay. So all I have to do is get rid of that.
Yeah.
As you guys probably know, I don't care about protons for these things. You guys have enough to learn and worry about. And keeping track of protons and balanced equations is tricky business and it's just not important. So while I see Seth's point, for those of you who aren't sure what he's talking about, don't worry about it. What I want you to keep track of is the oxidized form and the reduced form of both of these things. And you do want to make sure that they're both receiving the same number of electrons. That is important. If 2 electrons are being donated by NADH, they most certainly then have to become part of the reduced form of pyruvate. That's basically how we're going to do these calculations. Super, super similar, almost identical to how we calculated the phosphoryl transfer reactions between phosphorylated molecules in chapter 13, which is good news because you all did super well on that. Now I want to do another one. So in this reaction, which substance is losing the electrons? I know you don't have the table, but should be doable. That's right. NADH is going to donate electrons, and it's going to donate its electrons to O2, which is then going to become water, which is the reduced form. So what we want to do is first write out the half, these are called half reactions. Plus, what? Oh, no, you can fix them. I mean, I'm just going to put in generic arrows right now. Let's not worry about it. You're more than capable of doing that because you're so smart. Okay, then we're going to have 1/2 of 2. Now I have to go back to this table, figure out the reduction potential, and that's going to be positive 0.82 volts. Now, similar to the last example, we have to reverse the half reaction, the equation for the half reaction involving NADH. And we get a reduction potential of 1.12. Everyone good? Did I make a mistake?
It's
2032. Oh, I couldn't read my own writing. That's why. I see it now in the valuations. Terrible penmanship. All right, so hopefully everyone is good with this. You guys have a lot of examples. A lot of examples. I'm not going to go over this one with you because you guys know how to do this, but I just want to show you that half reaction tables can occur in all, or do occur in all of the biochemistry textbooks. And so this is one from, I believe, Leninger, maybe? But they're even saying, hey, this is coming from Handbook of Biochemistry and Molecular Biology from 1976, a long time ago. You can see it actually has, it's interesting how, number one, they put the positive reduction potential compounds on the top. It's the same thing. Now notice for oxygen, they get a value of 0.815, whereas we use a value of 0.82. And the reason why they're different is because the environment matters. Boy, oh boy, does it matter. So I gave you guys a couple examples here. Feel free to do them at your leisure. Okay, now I want to talk about how do we get from the change in reduction potential to a free energy value. So those reduction potential changes that we just calculated can easily be converted into delta G naught prime using this very simple equation, where you have N is the number of electrons, F is Faraday's constant, 96 kilojoules per volt per mole, and then the E naught prime is the reaction potential. And I want to put a box there on reaction potentials, not the reduction potential from those half tables. It's the reaction potential that we just calculated. So notice that for the example we just calculated, for the reduction potential for the transfer of electrons from NADH to molecular oxygen, we had a value of positive 1.14 volts. So if you put this into this equation, you're going to get a really, really negative value, telling me that that is an extremely favorable reaction, as we would suspect. Right? The transfer of electrons from a reduced molecule NADH that we know is going to fuel the formation of this unfavorable entity, the proton gradient, that energy change is going to be incredibly spontaneous, incredibly negative value for delta G naught prime for those electrons ultimately ending up to molecular oxygen. So effectively what I'm saying, there's a lot of free energy to play with. Now, if we go back and we calculate this, I don't have my calculator, so someone please do this for me. So calculate 1.14 volt times 96, which is Faraday's constant, times 2. It's like around, do you have your answer, David?
Yes.
What is it?
218.9.
218.9 kilojoules per mole. That's a lot of energy. So far, we've been talking about free energy changes for the hydrolysis of ATP as something special at around 30 kilojoules per mole. And this is like 7 times more energy. So what we're learning by performing this calculation is that the oxidation of NADH is going to ultimately release a ton of energy. And that energy can be used to create our proton gradient. And then I want you guys to perform this calculation as your homework. And this was using the previous learning check. By the way, if you have a reduction potential of 1.0, a change in reduction potential of 1.034 is a little less, isn't it, than NADH. So this is showing quantitatively what we already suspected, what I told you, that there's quite a bit more free energy available upon oxidation of NADH compared to FADH2. So that should give us a hint that the number of protons that can be pumped by the oxidation of FADH2 is not going to be as many or as impressive as NADH. Okay, so now what we can do in our last 15 minutes is start going through the electron transport chains. I want to dedicate Thursday as much as possible to ATP synthase. So we talked about this already. The electron transport chain has 4 giant complexes that each are constructed of multiple subunits, multiple polypeptide chains. And these have been designated complex 1, 2, 3, and 4. They have names. Complex 1 is now most commonly called NADH dehydrogenase. So you guys know what a dehydrogenase is, right? We've talked about dehydrogenases in glycolysis, in the conversion of pyruvate to acetyl-CoA in the citric acid cycle. And so this should tell you right off the bat, this complex is, even though it's a pretty crazy, huge thing, molecular machine, ultimately its job is going to be to catalyze the oxidation of NADH and to transfer those electrons to something, and that something is called coenzyme Q, or ubiquitin, another word for it. Complex 2 is also called succinate Q reductase. This is actually going to be the site where FADH2 gets oxidized. Interestingly, this is so in the citric acid cycle, we have 8 reactions. One of those reactions was the oxidation of succinate by succinate dehydrogenase. And what's pretty neat is that that enzyme actually is part of complex 2. So one of the things that kind of was like not intuitive to me when I was your age taking biochemistry is how do all these things live? And how are they organized? And it was very, at least the way my brain worked, since the citric acid cycle is a circle, I used to just kind of picture circles. But that's of course not really the case, right? And I want you guys to start thinking about the organization of pyruvate dehydrogenase and how there was so much logic to it, where we have this lipoamide arm that would reach over into the E1 active site and grab the acetyl group, and then go to the E2 active site and do its thing there, and then go from the E2 active site to the E3 active site, and so on and so forth. There's a real logic to the organization 3-dimensionally to all of these things. And we now know that for the most part, all of these enzymes are coordinated to at least some degree. So it shouldn't be a surprise to any of you that succinate dehydrogenase is part of the electron transport chain, because it makes sense. The job of succinate dehydrogenase is to transfer electrons from succinate to FADH2, which then ultimately are going to participate in the electron transport chain. So these things are just within proximity already, which is going to make this that much more efficient and fast. Okay, then we have complex 3, which is called Q-cytochrome C oxidoreductase. I know that sounds crazy. It's really not though. It's like the German language. The German language, I don't know if you guys have seen this, but German language has these words that are literally this long, and it sounds crazy, but if you break it down phrase by phrase of these words, you see that there's logic to it. So in complex 3, we have Q and cytochrome C. Q is going to be the reductant, and cytochrome C is the oxidant. So electrons are being transferred from reduced coenzyme Q to oxidized cytochrome C, forming reduced cytochrome C, and then oxidoreductase is another fancy word for dehydrogenase. And then complex 4 is called cytochrome C oxidase, and this is ultimately going to catalyze the transfer of electrons from cytochrome C, which we just discussed, to oxygen. That's going to form water. So I do think that, again, for all of you people moving on to professional schools, which if I remember all the way back in August when we met, seems like a long time ago, you guys are all going to have to take these exams, and so I want to make sure you're ready. It's part of the job. And so I would recommend that you are familiar with these names, right? And most importantly is the order in which they occur. So we'll get into that in a second. But first I want to show you what coenzyme Q looks like. So here it is in all of its glory. It's also called ubiquinone, by the way. This is the oxidized form, right? This is the form that doesn't contain those two high energy electrons from NADH or FADH2. And then this is going to be the reduced form. So notice that we have a carbonyl oxygen in this ring, in this conjugated ring, and ultimately those oxygens are the acceptors of electrons becoming OH. They also point out something here that's quite important. Those H's, or hydrogens, are protons. Remember, we're trying to generate a proton gradient here. Right? So you have to ask yourself the question, where are those protons coming from when we're going from ubiquinone to ubiquinol? And where do the protons go when we go from ubiquinol to ubiquinone? Because this is effectively a cycle. Let's look at some other stuff. In blue, they have this long alkyl chain. It's long because, look, we have brackets here, and we have 10 of these moieties, whatever you call them. I would refer to them as greasy carbon-hydrogen stuff. That's the technical term. So that's really, really long, making these things extremely hydrophobic. And that makes a lot of sense in terms of the molecular physiology, because coenzyme Q actually lives in the molecular membrane in mitochondria. The inner membrane of mitochondria is where coenzyme Q exists. So it's actually not soluble in water. It's soluble in the hydrophobic environment of the membrane. And that's why it contains these large tails that are completely hydrophobic. So when we talk about coenzyme Q, or ubiquinone, what are some of the important things to know? It's extremely hydrophobic. It's mobile, right? So it's not fixed in place. Think of a membrane. This is a lipid bilayer base membrane. You guys should have learned at some point that membranes consist of what we call phospholipids, where there'll be a phosphor group and a large hydrophobic tail. And the phosphate groups base water, and then the hydrophobic tails of the phospholipids come together, create a lipid bilayer. So this environment here is extremely hydrophobic. And so coenzyme Q lives in this space, and it can diffuse. Right? Just as if you think of me as coenzyme Q right now, and this room is maybe the top of the ceiling there is facing the inner membrane space of the mitochondria. The floor, underneath the floor, is the mitochondrial matrix. So two water or hydrophilic spaces, water-based or hydrophilic spaces. So I'm coenzyme Q, and you guys know I love to run around when I lecture, and so that's what coenzyme Q can do. It can just wander around the membrane freely. And that's going to end up being important because remember, coenzyme Q was the Uber, transferring electrons from one player in the electron transport chain to the other, facilitating those reactions. So it's going to carry electrons from complex 1, NADH dehydrogenase, to complex 3, which was the Q cytochrome C oxidoreductase, or from complex 2 to complex 3. And remember, complex 2 contained succinate dehydrogenase. And so we are going to see the transfer of electrons from FADH2 to coenzyme Q, forming ubiquinol, the reduced form. And then ultimately, that will go to complex 3, transferring electrons from coenzyme Q to this molecule cytochrome C. Now let's talk a little bit about cytochrome C, because we haven't talked about it yet. It is a water-soluble protein. So you should think of this as a globular protein, just like myoglobin, or any of the other proteins that we've been discussing. And its job is going to be to take the electrons that it got at complex 3 from coenzyme Q over to complex 4. And it's actually soluble, so it's not within the membrane. It travels in what we call the inner membrane space. So recall that if this is our inner membrane, and that's the outer membrane, we call this the matrix, and then this was called the inner membrane space. Yep, so this slide is just summarizing what I told you earlier. If we go from a fully oxidized Q and we start transferring electrons, we also have to protonate those oxygen atoms as they pick up electrons. So for instance, the first electron transfer event is going to result in the formation of what we call a semiquinone intermediate. So notice we have an oxygen atom that has an unpaired electron. We call that in chemistry a radical. And ultimately what's going to happen is when the next electron comes in, we're going to see full protonation of coenzyme Q, which we then call ubiquinol or QH2. So this is the easy way of talking about reduced coenzyme Q, QH2. Oxidized form is Q. Do you need to draw the structures in these things? No. Right? That's a waste of your memory capacity. So this is something you should memorize. You know? The pathways for the oxidation of NADH and FADH2. How do electrons flow in these systems? In the case of NADH, the electrons are going to enter at complex 1. They'll get transferred to oxidized coenzyme Q, which then becomes reduced. So we could actually add a little value to this table. Becomes Q2, which then will go to side complex 3, which will then generate Q and reduce cytochrome C, which then goes to complex 4, transferring its electrons to O2, forming 1. FADH2 works a little differently. It enters at complex 2, but remember, it doesn't really even enter, right? As we're about to see, complex 2 contains succinate dehydrogenase. So it's not like there is an entry or exit physically. It's just we're saying that the electrons from succinate will be transferred temporarily to FADH2 at complex 2, and then ultimately to coenzyme Q, generating QH2. And once it becomes QH2, everything else is the same. And the way this works energetically is that all of those reactions are favorable. They're all spontaneous. And the way you can see that is just by looking at these reduction potential tables. So let's look at NAD, which has a reduction potential of minus 0.32 volts. So the first thing we're talking about in the electron transport chain is the transfer of electrons to coenzyme Q. So we can see that NAD has a reduction potential of minus 0.32, whereas coenzyme Q has a reduction potential of positive 0.045. So if you calculate the reduction potential, it's going to be 0.32 plus 0.045, whatever that is, 0.365. And when you calculate the delta G naught Han for that, you're going to see it's going to be large and negative. That makes sense. And then notice that cytochrome C is going to exist below coenzyme Q on this table. And then cytochrome C exists above oxygen on this table. So we can think of the electron transport chain as like a game of hot potato, but where each reaction is energetically favorable, ensuring that the chain will ultimately go all the way to completion, where the electrons go from either NADH or FADH2 to molecular oxygen, their final destination. Okay, I'll see some of you at office hours, I assume, and then last